Hey kiddos, I got some questions on what is this free body diagram worksheet. So basically, it is just a worksheet to help you get some practice with boogers, free body diagrams. Very simple. So what you're going to do is basically redraw these pictures into your notebooks. Okay, so like draw all this in your notebook. You don't need all the words, right? Okay, what you do after that is you are going to, in this section, we are looking to determine the net force acting on each object. So if we take a look here, um, we have in situation A, we have forces that are going up and down. These are forces in opposite directions, so they are going to act against one another. If you remember, our axes in physics are typically up is positive, down is negative. Same sort of deal with left to right, or the x-axis. Right is positive, left is negative. So if we go through and we say, okay, there's normal force here, this is positive because it's going up. This gravitational force here, that is negative. So if we want to find the overall force in the y direction, like up and down, we're going to take positive 3 newtons plus negative 3 newtons. That will give us a net force in the y dimension of 0 newtons, meaning up and down, it's balanced. If we look, whoa, that was crazy. That's too much jazz for me. All right, if we look in the x dimension, we see a positive 5 and a negative 5. Okay. Those would cancel out. And so you'll probably notice that it's asking for a net force. I gave two forces. What gives? Well, the thing is, um, perpendicular forces do not interact with one another. So if I have this box and it's being pulled up by a rope with a force of 1 Newton, and the box itself has a force of gravity of 1 Newton, and then somebody pushes that box to the left with a force of negative 3 newtons, negative because it's going down, the box is just going to move to the left. It's not going to move up, it's not going to move down, it's going to move to the left because they're like the up and down does not affect the left to right. We learned that with projectile motion. Up and down, the y dimension does not affect the x dimension. Okay. So, I'll do one more of these, Johns. All right. So, let's look here. So the air resistance gives us a positive 40. Gravitational force gives us a negative 25. The net force, or if you'd like to call it the overall, yeah, well, we should call it the net force. That's what we should call it. F net, I'll say F net y, the y dimension, is 40 plus negative 25. 40 plus negative 25, or 40 minus 25, gives us 15. Lovely. Okay, so free body diagrams have 4 situations, blah, blah, blah. Analyze the results. Um, okay, so we know the net force. Okay, So basically, it's telling you what the net force is. Okay, I kind of see what it's trying to say here. So yeah, whatever, that's fine. Same deal. Okay, so it's saying we know here that the overall force. Ooh, I don't like that. The overall force, the net force, is 0. We know that um, left to right, we have 50 going this way. So what do we need to balance it out in the x dimension? Well, in the x dimension, we have a 0 net force because overall the net force is 0. So how do you balance positive 40? Well, you get, or positive 50. Positive 50 is over here. What do we need on the left side? Well, we're going to need another 50. It's just going the opposite direction, so it's negative. Same sort of deal here. We have 200 newtons going down. We need to balance it out because we have no net force. So how do you balance 200 down? Put 200 up. Okay. If we look at this second example here, we have a net force of 900 newtons going up. We have downwards 200. So what could you put up here that when you add this plus this would give you 900? Okay. So we could think of this as an equation, so the net force is equal to all the other forces combined, so F1, F2, blah, 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 so on and so forth. Okay? So in this case, you could say F net is 900. We know the downward force is negative 200. It's negative because it's downwards. Plus this other force that we don't know. Alright, solve for the one we don't know. Do some algebra. That gives you X, or the unknown force is 1100 newtons positive. Positive means up. That's good because that's the direction we want it to be. 1100 newtons. Okay. Alright, gonna get rid of this. Now we're looking at some of these word problems. This might be something nice to write down. Let's say let's do number 4. Ooh, magenta. Okay. So there's a girl who is hanging from a bar that's like held up by 2 ropes. Okay. So there we go. There's a drawing. But a free body diagram, we don't put these details in. I don't know why I drew all those details. So basically, we just need a box. This box represents the girl in the bar, right? And now we need to represent forces in this situation. Okay, so the girl in the bar are the box, because that's the object. What forces are acting on this girl? Well, we know that she is presumably on Earth, so she has a force of gravity. And it looks like there are 2 different ropes that are balancing out her force of gravity. So we have a force of tension from one rope and a force of tension from another rope. And together, all of them cancel out, meaning there is an F net of 0. So this force of gravity is canceled out by these. So there is no acceleration. She's motionless. Motionless. So no net force. Okay. Next we have a book that has a rightward force being applied to move it across the desk with rightward acceleration. Consider friction forces. So if the book is on a desk, that presumes that it is on Earth, so it's going to have a force of gravity. It does not say it is accelerating downwards, so we can assume that there is a normal force balancing out the force of gravity. So up and down, there is no net force, they balance out. The book is being pushed to the right, so that is the applied force or the push force. And it says that there is friction, but if the book is accelerating, that means the friction's probably going to be small. So it kind of looks like that. So overall, there'd be a net force from the push over here. Hail, hail. Okay, there, it's all back. All right, and let's do the last one real quick. So we got a car. It is coasting to the right and slowing down. Well, we're going to assume this car is on Earth, so there is a force of gravity. It does not say that the car is accelerating downwards, so we need to balance that force of gravity with the normal force. The car is slowing down, which means it has friction on it. But it doesn't say that it's speeding up, nor does it say it's at a constant motion. So it just says slowing down. So we can assume that the only force acting on it is friction, and that is acting to slow it down, even though it's still coasting forward. So that would be how we represent that. Okay. So this is all you're doing. You're just looking at how forces add up. Yep, that's about it. Pretty straightforward. How do we add up forces? If there is a force imbalance, like we have here, imbalanced forces, that causes acceleration. Unbalanced forces cause acceleration or change in velocity.